the last section in Module 3 of our OER Statistics class on probability. And in this course, in this section, we will look at tree and Venn diagrams. Specifically in this video, we will talk about tree diagrams. We have seen tree diagrams before. And before we continue, I want to remind you of the addition and multiplication rule of probability. First, let's focus on the multiplication rule for probability, which said the probability of two events occurring together, A and B occurring, equals the probability of A times the probability of B given A. And that could be that A occurred before B, or that we are, in the case of a contingency table, in the category for A, and we are also looking for B to be satisfied. In the case of our tree diagrams, things will happen, or we will make them look like they are happening sequentially. So one event will have happened before the other one. Of course, if the events are independent, the probability of B given A equals the probability of B, so we have the multiplication rule for independent events. So let's think a little bit about how tree diagrams have been used before. A tree diagram is a special type of graph used to determine the outcomes of an experiment, and this is how we used it before. What we're going to do now, we will also try to find, in addition to the sample space, the probability of every outcome in the sample space to occur. And the way we will do that is we will have branches, we will label the branches of the tree diagram with either the relative frequencies or the probabilities of the outcome we are pursuing on that branch to occur. Tree diagrams can make some probability problems easier to visualize and solve. So we have the same scenario here. We have an urn. It has 11 balls, 3 are red and 8 are blue. And we are drawing 2 balls from the urn. And in the first example, we will do it with replacement. And in the other example, we will do it without replacement. They are asking us to find the sample space, the probability of the same color, pulling the same color balls, and the other is the probability of different color balls. So let's think of how that looks like. So we have an urn, and it has 3 red, and it also has 8 blue balls. And we are about to pick 2. So we will assume that we will pick one first with, say, our right hand, and then we will put it back because this is with replacement, and then we will pick one with our left hand, and that will be the second ball. So we start here. We haven't done anything, and we are about to select our first ball, and it could be red or it could be blue. If it is red, we have probability 3 out of 11 to pick a red. And if it's blue, we would have a probability of 8 out of 11 to pick a blue ball. Whatever ball we pick first, this experiment is done with replacement. We will put it back in. So our urn continues to have 3 red and 8 blue balls. And now with our other hand, we pick a second ball. Now, the probabilities for the second ball would be, or the possible outcomes will be to be red or blue, whether we picked red the first time or if we picked blue the first time. So it's always the case that we will either pick a red or a blue. Now, in the first case that we have picked red, the probability of picking red again will be 3 out of 11, and the probability of picking blue will be 8 out of 11. Remember, this is with replacement. So if we have picked a red ball, we put it back in, and now we are drawing again from 11 balls. If we picked a blue ball, again we put it back in. The probability of picking red the second time will be 3 out of 11, and the probability of picking blue the second time will be 8 out of 11. The sample space are the possible ways we can reach one of the leaves of the tree. Leaves of the tree are the last outcomes possible after the last repetition of the experiment. The way to get to the top R would be from the start to get R first and R second. The way to get to the second row that says blue would be to go to R first and blue second. The way to get to the next R would be to pick blue first and then red second. And the way to get to the bottom, blue, would be to get blue first and blue second. This is the sample space. The sample space is red, 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 blue, blue, red, and blue, blue. The problem is that these events do not all come with the same probability of occurring because there are less red than blue balls. What are the probabilities of every outcome? We will use the multiplication rule to multiply the probability of picking red first, 3 over 11, times the probability of picking red second, which is 3 over 11. That is 3 times 3 is 9, and 11 times 11 is 121. Then to find the probability of red first and blue second, we will multiply the probability of red first times the probability of blue second, which is 24 out of 121. Blue first and red second comes with probability 8 over 11 times 3 over 11, which is 24 out of 121. And the last one, which is blue and blue, has probability 8 over 11 times 8 over 11, which is 64 out of 121. If I have done a good job, when I add 9 plus 24 plus 24 plus 64, the sum here should be 121 out of 121, which is 100%, and that will cover the whole sample space. Now, the probability of picking the same color is the probability of having red, red, or blue, blue. And red, red, or blue, blue are actually mutually exclusive events. You will either pick red first and red second, or blue first and blue second. And when they are mutually exclusive events, we add their probabilities. So the probability of either 2 reds or 2 blues will be the probability of 2 reds plus the probability of 2 blues. And that will be 9 out of 121 plus 64 out of 121. They have common denominator, so this is 9 plus 64 out of 121, which is 73 out of 121. What's the probability they will be different color? Will be the probability of red-blue or blue-red. These are also mutually exclusive. I can either pick red first and then blue, or I can pick blue first and then red. And that is 24 plus 24 out of 121, which is 48 out of 121. Also, same color and different color balls are complements of each other. So the probability of different color is 1 minus the probability of the same color, and the probability of the same color is 1 minus the probability of different color. So 73 plus 48 should also add to 121. So this is the same story, only now it is without replacement. So without replacement means that I start with 3 red and 8 blue. I pick up my first ball, and it could be red or blue. The probability could be 3 out of 11 for red and 8 out of 11 for blue, but I will hold the ball that I picked with my one hand, and I'm going to reach it with my other hand to grab the next ball. Now, if I have picked a red ball, my urn has now changed, because in this case, I will have 2 reds and 8 blues. I am holding the third red ball in my hand. So when I do my next pick, which could be either red or blue, the probabilities have changed. The events are dependent. Now the probability for red is 2 out of 10, and the probability of blue is 8 out of 10. If I had selected the blue as my first ball, then the urn also has changed. It has 3 reds, but it has only 7 blue, because the 8th blue ball is in my other hand. So when I reach to pick the second ball, which also could be red or blue, the probabilities have changed. Red is 3 out of 10, and blue is 7 out of 10. The outcomes have not changed. The outcomes are still red with red, red with blue, blue first and red second, or blue and blue. The sample space looks the same. Red, 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 blue, blue, red, and blue, blue, but the probabilities are not the same. So what's the probability of getting 2 red balls? It will be 3 out of 11 times 2 out of 10, which is 6 out of 11 times 10 is 110. Red blue will be 3 out of 11 times 8 out of 10, and that is 24 out of 110. Blue red is 8 out of 11 times 3 out of 10, which is 24 out of 110. And finally, blue and blue is 8 out of 11 times 7 out of 10, and this is 56 out of 110. These 4 outcomes are actually mutually exclusive of each other. So if I have 2 reds, I cannot have a red and a blue. If I have 2 reds, I cannot have a blue and a red, etc., etc. And if you add them, and if we have done a good job, it will be 110 out of 110 for the probability of everything in the sample space being 100%. 1. What's the probability I get the same color? Well, the events are still the same. I'm looking for the probability of red, red, or blue, blue. And now I'm going to add those probabilities because the 2 events are exclusive of each other. So it will be 6 plus 56 out of 110. And that will be 62 out of 110. What's the probability of a different color? Will be probability of red, blue, or blue, red. And that will be 24 plus 24 out of 110 equal to 48 out of 110. In the next chapter, we will revisit this problem, but it will look a little different. So it will look like this. A box has 3 defective and 8 good cameras. We pick 2 cameras to test, and here the without replacement is implied, so it's not going to be mentioned in the problem. Find the sample space and the probability of each outcome. Then find the probabilities below. So if you remember from the previous example, it is with replacement. We don't have red and blue. We have defective and good. So when we start, we can choose a defective or we can choose a good camera. The probability for defective will be 3 out of 11 and good will be 8 out of 11. And then when we have picked the first camera, the probability, the chances are, or the outcomes are, to do a defective or a good for our second pick, or if we have picked a good camera, to do a defective or a good for our second pick. Remember again that it's without replacement. If the defective is in your one hand and you are reaching with the other hand to pick another defective, it will be 2 out of 10. But if you pick the second one good, it will be 8 out of 10. If you are holding a good camera in your hand, you have only 7 good in the box, so you will have 3 out of 10 chances to get a defective and 7 out of 10 to get a good camera. The sample space is defective and defective, which is the first row here. Defective and good, which is the second row here. Good and defective, which is the third row here, or good and good, which is the last row. And the probabilities are the same values that we found in the example of the urn. Now, the probability of no defective means that you picked only good cameras. So the probability of 2 good cameras will be 56 out of 110. The probability of 1 defective will be that you either picked a defective and then good, or that you picked a good and then a defective. So that will be 24 plus 24, which is 48 out of 110. And the probability of 2 defective will be that you picked a defective and then a defective, and that will be 6 out of 110. And again, you want to double check that 56 plus 48 plus 6 do indeed add to 110 out of 110, so that you have all the possible scenarios for the outcome of what happens when you pick 2 cameras out of the box.